Hello, my name is Cameron Castles and welcome to my video presentation for Math 3033 Geometry. In this presentation I will demonstrate the result from class that 5 points determine a conic, and I'll be doing this via a geometric construction. In projective geometry, we find just as 2 points determine a line and 3 points determine a circle, it takes just 5 points to determine a conic. Formally we say, if 5 points are in general position, that is, no 3 are collinear, then there is a unique, non-degenerate conic associated with those points. I will now demonstrate this result using the Breckenridge-Maclaurin construction. We start with Pascal's theorem, which states if 6 arbitrary points are chosen on a conic and joined by lines to form a hexagon, then the 3 intersection points of opposite sides are collinear. The line on which these intersection points lie is known as the Pascal line. So here I have a circle on which I have picked 6 arbitrary points, and you can see I've color-coded the opposite sides, and I've marked their intersections and plotted the Pascal line for this circle, or for these 6 points, rather. And as you can see, those 3 points are collinear, and these points are completely arbitrary, so if I move them around, this is always going to be a straight line. And that is because the circle is of course a conic. I should note the special case where all the opposite sides of the hexagon are parallel. Now, since we are working in a projective geometry, we know that parallel lines intersect at infinity, which means that all 3 of these opposite pairs are collinear on the line at infinity. That is, the Pascal line is the line at infinity in this case. The converse to Pascal's theorem is known as the Breckenridge-Maclaurin theorem. That is that if the 3 intersection points of opposite sides of a hexagon are collinear, then the 6 vertices of the hexagon lie on a conic. It is this theorem which forms the basis of our construction. Okay, so here I have 5 points in general position, and I'm going to use them to construct the unique conic that is associated with them. So what I'm going to do is pretend that there is a point here between A and B, our 6th point, so that we can use the Breckenridge-Maclaurin theorem. That would make A and D and B and C a pair of opposite sides, so I'm going to draw those lines in. And this is our first intersection line for our Pascal line. Now for our next pair of opposite sides, we have EC, and the other side would be A to our 6th point. Now we are able to select this arbitrarily where this intersects, so I'm going to pick here. And what this now allows us to do is put in our Pascal line, like so. Now finally we can generate our 6th point. So we have the final set of opposite sides. We have ED here, and we know that B must intersect the Pascal line at the same point as its opposite side. So we'll trace like so. And now this has generated our 6th point here. Now note that our point here, G, was placed arbitrarily, which means that this 6th point, I, is also arbitrary, dependent on G. So watch what happens when I add tracing to point I, and I begin to animate point G. We see that it begins to trace out an ellipse, and this is the unique conic that is associated with those 5 points. And you can see we only generated it using those 5 points. Everything else fell out of those 5 points. I've moved the 5 points around a bit to imply another shape. They are in general position again, so they should generate a unique conic. So I'll animate G again, we'll see what happens. And we see that point I begins to trace out a hyperbola. Now for the case of a parabola, I have to choose my points a little more carefully because the parabola, of course, is the conic where the eccentricity is exactly 1. So I've plotted out a parabola here, which I will hide, and on it I've selected 5 random points, and I've done the construction that I demonstrated before. Now we can see again, as I put tracing on I and animate G, we get a parabola. So to explain this construction more thoroughly, we start with our initial 5 points, and out of those 5 points we've generated this intersection point G, which was arbitrary in our construction. And as a result of that, we generated our 6th point I. And because G was arbitrary, I can take any place, anywhere on the conic that is unique to those lines. So when we animate G and we trace I, we are tracing out that conic and all possible points on that conic. So this construction has demonstrated that if 5 points are in general position, then there is a unique non-degenerate conic associated with those points. And we have constructed that unique conic using only those 5 points. And that concludes my video presentation.